permission, can we start?
Please, kindly start. Sure. Kindly go ahead.
Okay. Thank you, Father. Good afternoon, respected Father Principal, Reverend Dr. Dominic Savio SJ, our esteemed speaker today, Professor Subir Kumar Das from JNCASR Bangalore, respected dignitaries, professors, my dear students, and dear alumni joined across the globe. A warm welcome to Spectrum 2022, organized by the Postgraduate and Research Department of Physics, St. Xavier's College Autonomous, Kolkata. This year marks the 13th edition of Spectrum, the annual feast of the department. Every year, Spectrum brings with itself the joy of celebration of scientific curiosity and creativity in form of talks, debates, and a vast array of intellectual activities among the students of different institutions of Kolkata and outside the state. So Spectrum is beyond the monochrome. From the last year, Spectrum brings us a mixed feeling. While organizing the Spectrum, our beloved Nilangshu Saha's memory comes to our mind always. Nilangshu is the source of our inspiration to fight against all the odds. He will remain in our hearts forever. May his soul rest in peace. Last 2 years at Xavier's, we fought together against all the challenges posed by the unprecedented pandemic condition. Inspired by the vision of our respected Father Principal to bring back the students to normal academic activity, we have not only continued our teaching learning process in the department, we also hold various national and international webinars and the departmental colloquium and programs to boost the morale of the students. Entire department stands together as a team to continue the rich legacy of our esteemed physics department. My sincere thanks to all the faculty members of the department, support staffs, and the students for their active involvement in all development activities of our department. My sincere gratitude to our Vice Principal and the Deans for their constant guidance and support. My heartfelt gratitude to Father Principal, Reverend Dr. Dominic Savio SJ, for his inspiring, wise leadership and wholehearted support and encouragement to all of us always. Thank you, Father Principal. Now, without wasting any time, I request our respected Father Principal, Reverend Dr. Dominic Savio SJ, to deliver his inaugural address. Father Principal.
Thank you, Professor Indranath Chowdhury. Professor Subir Kumar Das, Professor Indranath Chowdhury, the head of the Department of Physics, Postgraduate and Research Department of Physics, respected faculty members, alumni, our dear students, a very good afternoon and a very warm welcome to everyone present here, especially our distinguished guest today, Professor Subir Kumar Das of Theoretical Sciences Unit in Jawaharlal Nehru Center for Advanced Scientific Research. It is our great honor to have you, Professor Subir Kumar Das, and also the teachers and our students. It is my immense pleasure to see the sustained efforts of the Department of Physics in collectively organizing the departmental events. All the students have worked hard diligently in putting forth such an interesting and highly anticipated event, Spectrum. The professors have also worked meticulously besides the students. The same is highlighted in the systematic planning of the events. I know Spectrum has been a huge success in the previous years and has invoked participation in events from the student community of different departments. I hope this tradition is carried forward and this forum continues to promote interdepartmental interaction across all science and art fields. This shows the need and importance of collaborative nature of scientific work and growth of scientific temperament. Not everything is about achieving your goals, but also the sheer excitement in unraveling the mysteries of this world. I would like to encourage students to avail of all the exposure that the department has to offer, and at the same time interact with the postgraduate and research scholars of the department. Finally, once again, I would like to congratulate the department and to Professor Indranath Chowdhury for taking a lot of initiatives to make sure the students get maximum benefit when they are in their college, and for their extraordinary efforts in teaching, and all the faculty members for their extraordinary efforts in teaching and research. I welcome once again all the dignitaries and the participation, and we are very, very grateful for the time given by Professor Subir Kumar Das for us this afternoon. I would like to wish this edition of Spectrum a grand success. May God bless you. Thank you very much.
Thank you so much, Father Principal, for your gracious presence today and kind words of encouragement. Now it's the time to launch Horizon, the annual departmental magazine, which is a place where the students and the professors pour in their creativity. Horizon has come a long way, with this year making the 13th edition. Thus, without further delay, may I request Father Principal to officially launch the 13th edition of Horizon and say a few words. Father, kindly, this is now they are showing it in the background, and just with in your presence, we are, you just bless it.
Yeah, sure. So my congratulations to all the students and the teachers for bringing out such a wonderful journal of the department of, for the department, the Postgraduate Research Department of Physics, the Horizon. And I'm sure that in coming years, this magazine, will evolve into a research journal, maybe a UGC research journal. I think Department of Physics has got a lot of potentials to, make this magazine into a research journal. And I wish you all the best. May God bless you. Thank you. Thank you very much.
And it's basically brainchild of Professor Shorbori Guho. So now may I request Professor Guho to come and say your experiences about the spectrum, the Horizon that you have initiated 13 years back. So Professor Guho, kindly come and say a few words, and then we'll close this section and then move on to the next one. Professor Guho.
Thank you, Dr. Chowdhury. Thank you, Father Principal, and all my colleagues, all my students, all other staff of St. Xavier's College, my students previous and present. Thank you for inviting me to share my thoughts on the occasion of the release of the 13th edition of Horizon, which incidentally coincides with the 13th edition of Spectrum. Spectrum has been held in the department beginning from 2009, when I was the head of the department, with only a gap in 2020 due to the sudden suspension of classes in the middle of March 2020. Spectrum 2009 was held on 4th March 2009. In fact, the launch of Spectrum led to the launch of Horizon, as we, the teachers, and most importantly, the students, felt the urge to record the events taking place in the department in the form of a magazine. Thus, the first edition of Horizon was released in November 2009. The second edition, however, was not released in November 2010, Instead, its release was pushed back to March 2011 when the third successive spectrum was held. Thus, Horizon started lagging behind Spectrum, and that continued till 2019. The pandemic has removed this lag. I wish that both the departmental annual event, that is Spectrum, as well as the annual magazine Horizon, continues to flourish and grow with time. I'm so happy to be here with you and to see at least that both this Spectrum and Horizon has at least continued for 13 years, and maybe it may continue to grow for multiples of 13 years in the future. And I finally thank you once again to end my note and my thoughts sharing here.
Thank you, Dr. Guho. Thank you, Father Principal, for your precious time. So now, before moving to the next section, I call upon Raktim Mukherjee, a second-year physics honors student, who will be the host for the next part of today's program. Raktim, please take over.
Thank you very much, sir. And thank you, Father. And thank you, SG ma'am. Good afternoon to one and all present here. I'm Raktim Mukherjee, your host for today. As Professor Chaudhary mentioned, and I'm again saying this with a heavy heart, that we lost a very dear student of our department, Nilanshu Saha. He may have gone from our sight, but never from our hearts. I would like to request Dr. Tonaya Bhattacharya to say a few words.
Thank you, Raktim. Nilanshu joined our department as a first-year BSc student in July 2018. It is always a pleasure to see the newcomers in the department getting tuned to the melody of the college. We noticed Nilanshu as a super energetic boy in the physics lab and in the theory classes. During the lab classes, he was running from one table to another, as he always had a lot to share with his batchmates. Nilanshu's bandaged hand, his occasional absence in classes were left unnoticed for quite some time under the cover of his infectious energy and enthusiasm. As days passed, we came to know that Nilanshu was fighting with alveolar rhabdomyosarcoma. Nilanshu's indomitable spirit and energy in every domain of the departmental activities were unparalleled. I remember interacting with him during the organization of Spectrum 2020. He had to be admitted in the hospital in between, but the interactions, discussions, and planning kept on going. The day when the college had to be closed with the onset of the pandemic and Spectrum had to be cancelled, Nilanshu and his friends were completely heartbroken. All their efforts in organizing Spectrum could not see its culmination. That was the last time I met Nilanshu on the corridor of St. Xavier's College. Nilanshu taught us how to squeeze out happiness and positivity from every living moment of our life. He was the symbol of happiness, sincerity, and passion. His smiling face and bright eyes were always protecting us from the suffering and pain he was going through. Nilanshu, we are lucky to have you among us, and your bravery will always be an inspiration.
Thank you so much, ma'am. So, for the next part of today's program, we have a lecture in honor of Nilanshu Da. We have with us Professor Shubhil Kumar Das, who will deliver a talk titled Mpemba Effect. Is it common? I would like to request Dr. Shivaji Banerjee to introduce the speaker. Everyone is requested to keep their videos off and audios muted during the proceedings.
Hello, everyone.
Yes, we can hear you.
Okay, thank you. Let me start by sending my respects and love to all the members who are present here on the dais, for the principal and the HOD and all the students who are here. I also would like to send my regards to Father Yunji Lafont, who was born on this day and who continues to be an inspiring figure in the Department of Physics. Today is my friendly task of introducing all listeners to the speakers of the Spectrum 2022, the colorful annual event of the Physics Department. I remember having met him on our campus some years back, and it brings back nice memories. It's very nice to see you back here, Shubit. Dr. Shubit Das did his bachelor's and master's degree in physics from the University of Calcutta. He did his PhD with Professor Sanjay Puri, JNCSR, in 2002. During his postdoc days, Professor Das worked with Professor Kurt Binder, Eugen Horbach, as well as Michael Fisher, who are all very illustrious physicists known for their contributions in the physics of phase transitions and Monte Carlo simulations. Dr. Das joined Jawaharlal Nehru Center for Advanced Scientific Research in 2007. He had been a DST Ramanujam Fellow, an associate member of ICTP Trieste, visiting scientist in the University of Mainz, University of Düsseldorf, Germany, École Normale France. He have held many invited positions on the prestigious Booty Foundation Award of the Indian Physics Association and has been serving regularly either as member of the editorial board or as referee of international journals. Professor Shubit Das is an active researcher in the field of statistical physics of living and non-living matter and has numerous solid publications in referred international journals and leads a team of avid young researchers. It is quite an opportunity for all of us, students and faculty alike, to hear him this close and clear. Without any further delay, I would like him to take the stage and speak out to the eager and expectant audience. Thank you very much.
Well, thank you, Shivaji. I obviously remember meeting you. I wish I were there, as I was telling the father. Anyway, let me start by thanking the father principal and Indranath and Shivaji for the organization and kind invitation to the important event of the physics department of St. Xavier's College in Kolkata. And it's indeed a proud moment for me to be part of the celebration of this historic college, having extraordinary list of alumni as well as past and present faculty members of outstanding caliber. Indranath had invited me for this event in the year 2020. You all heard from various people that the event was about to take place, and then because of COVID, it was cancelled. And when it was about to be cancelled, I heard the story of Mr. Nilanshu Saha from my friend Indranath. He was very ill at that moment, and nevertheless, he was very, very actively involved with the organization despite his illness. Naturally, he was very sad when people are saying that it may get cancelled. Life is short, and for some people, it is much shorter. But I never thought that I have to give really a memorial lecture that is named after him. In any case, life sometimes is like that. Coming back to my lecture, it is possible that some of my teachers are also present in the audience. So it's a kind of nervous moment for me to give a lecture in front of this audience. It's kind of feeling like I'm writing my exam again. Okay, and given that this is a happy occasion, it's an annual event of the college. It comes once in a year. Because of that, I do not want really to show slides full of equations. But I will tell you a story, an inspiring story of a student from one of the African countries. Okay, so with that, I start sharing my slides. One of you, please speak up if you cannot hear me. Okay.
It's perfect.
Okay, I start by showing you a video. You can see my email screen, right? That's nice, right? Okay, back to my slides. So what you saw in that video, that's a YouTube video that defines the Mpemba effect, the subject matter of my talk today. The title specifically is Mpemba effect, is it common? So here is the outline of my talk. I will give a brief introduction to Mpemba effect. I will tell you about the history, definition, etc. Then alongside, I will present some results from my group and then finally conclude. Yeah, so this is kind of same thing in picture. What I have shown in the video. So what is happening here, a person is throwing boiling water into the air and the temperature there is very, very low. Okay, it's below minus 20 degrees Celsius. And what you have observed in the video or seeing in this picture is water after being thrown, it is getting converted into ice. And if you repeat the same experiment with room temperature water, okay, the conversion of ice will not happen within the time scale by the time the material or water reaches the ground. So you will not be able to see such beautiful picture, and that's what is Mpemba effect. Okay. So now let me start with the story. So what I showed via this, I tried to convey via this picture or that video, that's very recent, last year's observation. Now, let me go several decades back. The picture that you show, that you see on the screen, that is of a then school student. His name is Erasto Mpemba, Erasto V. Mpemba, and he's still alive. He's in 70s, and he was a student in 1963 in a high school in Tanzania. And there was a cookery class, and he, along with his friends, were asked to prepare ice cream. And because of certain reason, he needed to put a hot mixture. I mean, when you prepare ice cream, what you do, you make a mixture of milk, sugar, and probably a few other things. Some of you can tell me better than what I know. Anyway, so you have such a mixture and put inside the refrigerator, and after a while, you see that some phase change has happened, and that's what is ice cream. Okay, but because of so Mpemba was late and one of his friend was kind of occupying the refrigerator, so he couldn't put his ice mixture quickly, and there was some time limit to prepare the ice cream. So what he did, what typically people do, you basically heat up the milk so that all the bacteria, all the germs are gone, and then that's my logic why it is heated, and then you bring it down to room temperature and then do the preparation and put it inside the refrigerator. But by the time Mpemba could only heat up his milk, but there was no time to cool it and bring it down to the room temperature before putting it inside the refrigerator. So that's what he did. He had to put a hot mixture of milk and sugar inside the refrigerator. And what he observed is the following. His hot sample froze faster than his classmates, whose mixture was at room temperature before putting inside. And then this is very, very surprising observation. You ask the question generally then, if two identical bodies of liquids, say water, by the way, water and milk share a lot of phase-transition related properties, okay, including the freezing point, boiling point, critical temperature, etc. Okay, so the question is, if two identical bodies of liquids, say water, with different temperatures are placed inside the refrigerator, which one will freeze first? My belief is that the common answer will be colder one, the one that is colder to the temperature where water freezes or milk freezes. But this observation was contradicting this expectation. That's quite nice. Naturally, Mpemba's observation was not believed by his friends and teachers, and they said, some of them, you're confused, it cannot be correct. Then after some months or so, Dennis Osborne, then an somebody is talking. I do not know who. I mean, you can hear me?
Yes, yes, should be there.
Okay. Yeah. So then, some months later, Dennis Osborne, an English gentleman, he passed away in 2014, and then a university teacher in Tanzania. Later, he became a diplomat, from academician to diplomat. In any case, so this gentleman, this teacher, university teacher, was visiting Mpemba's school to deliver a physics lecture. And at the end of the lecture, completely out of context, Mpemba asked for an answer to what he had observed. And no doubt his friends and teachers felt embarrassed when Mpemba asked the same question to this university teacher. And then it was kind of, this phenomena was unknown to the teacher. And after returning to his university, to his office, Osborne asked his assistant to repeat the experiment, to do the same experiment with water. And Osborne's assistant said his observation was same as Mpemba's, but he promised to Mr. Osborne, to his boss, that he would continue doing the experiment until the correct result is observed. It's very nice and interesting statement or fact. Then later they did some more controlled experiment, and the results were published in this paper called Pools by Erasto Mpemba and Dennis Osborne, that was published in a not so high profile journal. It's called Physics Education. And here is the plot of the starting temperature of water and the time to start freezing. Okay. So you can see as the initial temperature decreases, so of course you quench the water sample from various different temperatures to a common final temperature, which is below 0 degrees Celsius. Okay. If you do it at 0, then you are in a little bit of trouble. I'll come to that point later. So as the starting temperature decreases, you can see that the time to freeze increases. So hotter the starting temperature, quicker the freezing occurs. Okay. So in a nutshell, in brief, that's what is happening. You have hotter sample of water and colder sample of water, and then put both the samples to a common final temperature below 0 degrees Celsius inside the refrigerator, and then you observe that the hotter one froze faster than the colder sample. Okay, so that's what an initially hotter body of water freezes faster than a colder one. That's again the Mpemba effect. Same fact I stated in a slightly different way after stating some facts on history. So we'll go back to the history again. Before that, let me tell you that there are controversies regarding this observation or fact. Several groups contradicted it, even very recently. So this particular paper that was published in 2016 had the title Questioning the Mpemba Effect, and the subtitle says hot water does not cool more quickly than cold. Okay, this is the title. And in the abstract, in some place they mention, we conclude somewhat sadly that there is no evidence to support meaningful observations of the Mpemba effect. But there are difficulties with the experiment, so these authors should not be blamed. Okay, I will come to those points and difficulties. And coming back to the same picture that you showed in the second slide, against that I say that I believe such open-air experiments have put the doubts into rest. Now, it is not Mpemba who observed the effect first. He actually rediscovered the phenomena that kept on being forgotten from time to time. Actually, historically, the phenomena dates back at least to Aristotle. It was discussed by Aristotle, it was the Greek philosopher, it was discussed by Descartes, the French scientist of the 16th century. Okay, and you will get a good account of all this information in Wikipedia. The basic fact, let me tell you again, when placed inside a refrigerator, an initially hotter body of water freezes faster than a colder one. Very surprising, no doubt. And what it means in more simple language, that will state you why it is even more, it is so surprising. So today, there is spectrum at Park Street in St. Xavier's College. I borrowed this picture from Wikipedia, the St. Xavier's College logo. I think it is the same logo even now. Now, let us suppose, let us say that there are three students who want to be part of this event called Spectrum in St. Xavier's College in Park Street, and they want to be physically present there. Let's suppose that it's happening offline. Okay, so one starts from Shialda, another from Kalikapur, and another from Barakpur. Okay, so the name Kalikapur I took because my friend Indunath lives there. Okay, and anyway, so Shialda is, I was checking on internet, Shialda is roughly about 4 or 5 kilometers from Park Street perhaps, and forgive me if I'm wrong. Then Kalikapur is about 20 kilometers and Barakpur is about 40 kilometers. Okay, roughly, let us accept that. Okay, and they're into race who can reach the location of Spectrum earlier than the others. And here is the result of the race. C is the earliest to reach, then B, and finally A. So it's like when you start with a hotter body, it's further away from the equilibrium in the frozen state. Okay, so if you are starting from say 1 degree Celsius and somebody else's water sample is at 90 degrees Celsius, certainly 90 degree one is much further away from the equilibrium at the frozen state. Okay, so that way it's very surprising. And even then, so this very unlikely outcome of the race is possible if there exists different modes of transport for different people, different students or faculty members. For example, if C travels in a helicopter, then B in a car and A walks. Okay, then this outcome is possible, and something similar may happen in materials also, with water or milk also. But the question is, in materials, how different temperatures are leading to different arrangements of transports. And this needs intervention of sophisticated theories and simulations. And then after this example, let's go back to the case of water. for making ice, liquid water, so I'll tell you about some certain difficulties. For making ice, liquid water is kept inside deep freezer with temperature much less than 0 degrees Celsius, which is the freezing point. Okay, this we all know. And this choice of much lower temperature, typically you put in deep freezer, it's either minus 18 degree, minus 20 degrees Celsius. So when you go to the supermarket and buy, say, a packet of chicken or some paneer, you'll see that the temperature is below minus 18 degrees Celsius. Okay, and this has connection with metastability. Now let us try to understand what metastability is. It's related to the fact that a system is not at equilibrium that is expected for the provided thermodynamic or environmental condition. Okay, so there is always some delay in homogeneous nucleation. Okay, and presence of impurity may help a system get out of this metastability. Okay, so again, coming back to the point of the definition of metastability, a system is not in the thermodynamically favorable state, rather it is stuck into, say, for example, you are quenching or putting a glass of liquid water inside the refrigerator at 0 degrees Celsius. Ideally at that temperature you expect it to freeze to ice, but it doesn't happen. Okay, for that you either need to lower the temperature much below 0 degrees Celsius, or you can add some impurity that may help a system get out of metastability. And then the question is, what is metastability? Okay, so these are basically nucleating agents. I'll give an example or of impurity in a slightly different way. Suppose you are in the Kolkata book fair, and the population density of people throughout the Mela ground is, say, uniform. And all of us, so uniform means there is no nucleation, there is no cluster formation. Okay, and all of a sudden a film star arrives. I mean, it depends upon who you like. You may like Dev, or you may like Prosenjit, or you may like some actress. Whatever it is, film stars are much more attractive than physicists. So he or she is different from others. They can attract people, and they're naturally an impurity. Their property is different from others. Okay, that's why they are impurity, and their attractive ability helps nucleation. There will be nucleation or clustering around him or her, and this goes by the name of heterogeneous nucleation. Okay. So such kind of metastability related problems exist in experiments as well as in simulations, and that leads to a lot of difficulty in both experiments and in computer simulations. And also there is no satisfactory theoretical understanding of Mpemba effect. Only in last decade people have started investigating it. The theoreticians started investigating it. And in fact, in the year 2012, a competition was arranged. It was held by the Royal Society of Chemistry in London, and Mpemba himself, and also, I guess, Osborne. So this is the picture together. Mpemba looks like this now. He used to look like this in 2012, and this is Osborne. And they were present to give away a prize for best explanation of the effect. So from this, you can get some idea that the understanding of this is very premature. And I'll be presenting some results from computer simulations. So for that, let us try to get some idea what is done. First of all, computer simulations also suffer due to metastability, and most models provide ice only in contact with surface. So this is again related to heterogeneous nucleation. And there are several different types of models of water. So water, you know, it consists of 2 hydrogen atoms, or it can be some other isotope of hydrogen. And then there is 1 oxygen atom. So there are various different types of models depending upon how many charge points you assign. And I have copied this picture from Wikipedia. And then this various different, so you can construct 2-point model, 3-point model, 4-point, 6-point, like that, how many points have charges. And then those charges and the atoms, they interact with each other via the Coulomb as well as Lennard-Jones potential. And with this model, you perform typically molecular dynamic simulation, and there what you do, you basically solve the Newton's equations of motions. Okay, and surprisingly, to our knowledge, to my knowledge, there has been no conclusion in the literature from water computer simulations. And in experiments, even if the ice nucleation, that's what I write here, takes up to microseconds, it is very difficult to reach that time scale in computer simulations. Okay, several 100 nanoseconds is also extremely difficult. And that time scale gets shortened drastically when you consider increase your system size. So here are some results. I have been pursuing the problem along this direction for water with my student Shomik Ghosh. So with very few particles actually. Then we'll apply some finite size the scaling type of theory to understand the results in future. So this is your configuration of your water body at very high temperature, and you quench to a very low temperature. So you basically move from disordered configuration to crystalline state. And when this occurs, there is a jump in the potential energy. And this work is in progress, so I won't say too much about it. Rather, let me restate the fact that we have a major problem in hand. It's not that I have a major problem in hand. Those who are working in this direction, along this direction. So basically, more and more people are participating. And then you ask the question, have we defined the problem accurately? With respect to that, there are 2 points I should mention. So you start from say 100 degree or 99 degree or 80 degrees Celsius and put your water inside the refrigerator. Then there are 2 facts. One is how long it takes for the temperature to go down to that temperature, the lower temperature, final lower temperature, and then the freezing. Okay, so there are 2 facts. So one is rate of fall of temperature. That depends upon the starting temperature. I mean, you heard of Newton's law of cooling and all. And often interpretations are provided by adopting this particular angle. What I stated, I'm restating again. I wrote how long it takes for the systems to arrive at the new temperature. So here are some key words. For example, hotter body, faster evaporation, lower remaining mass to cool down to a certain temperature, latent heat due to evaporation, etc. But all these remain unsatisfactory. And another angle, basically, how long does it take for the phase transformation starting from different state points for instantaneous quench? Instantaneous quench means you assume that the system assume the final temperature instantaneously, immediately. So that is a very much theoretical concept. But people are adopting that angle. I mean, just that basically discards the time taken by the system to reduce the temperature from the starting high temperature to the lower temperature, lower final temperature. So the rest of the talk will cover discussions on such instantaneous quench. And then there has been an effort to generalize the effect or the phenomenon. You basically take any system, not necessarily water, and ask the question, is there any dependence of the relaxation time on initial temperature for reaching the equilibrium corresponding to the final quench temperature? So you ask the same general question for any system. And the people are taking various different types of system, and one such system I mentioned here, recently studied system, is the spin glass system, and there people did observe, and this is a paper in which Giorgio Parisi, one of the physics Nobel laureates of this year, he is also an author. The title of the paper is Mpemba effect in spin glasses is a persistent memory effect. And in such spin glass systems, you have interactions, basically combination of ferromagnetic and antiferromagnetic interactions that gives rise to frustration, and that can lead to metastability in the system, the kind of things I have discussed in previous few slides. Okay, and not only the mixture of ferromagnetic and combination of ferromagnetic and antiferromagnetic interaction. Only antiferromagnetic interaction can also lead to frustration. And one such work is by Lu and Raz, and the title says Non-Equilibrium Thermodynamics of the Markovian Effect, Mpemba Effect and its Inverse. I'm not going to get into the subject matter of these papers. Just these are some examples, and to tell you that these are more complex systems, probably less complex than water. I'm not sure. I mean, water we drink, everybody. I mean, every day so much. It is consumed so commonly, but we know very little about water. It's a very, very complex system, by the way. And these systems perhaps are simpler, but not as simple as what we have considered. We asked the question in the context of a much, much simpler system, that is an uniaxial ferromagnets. And this system can be modeled via the very well-known nearest neighbor Ising model. Okay, the Hamiltonian of the Ising model is this. So you have spins Si and Sj. They can take values +1 and -1. Okay, and +1 corresponds to upward direction, upward orientation, and -1 is downward orientation of a spin, and they interact in this particular way. That's how the Hamiltonian is written. And Jij could have been anything random, whatever. But here we take Jij to be constant for all pairs. They are same. And this Ij, typically for nearest neighbor, you put this Ij inside angular brackets, and that is understood here. So these are nearest neighbor interactions. So as simple as my Ising model can be. And then we prepare the systems at various different temperatures. Before that, let me tell you, so in the water case, there is a phase transition, and here also this Ising model, let me tell you briefly the history of Ising model first. This model actually completed 100 years in 2021, and it was given by Lenz and Ising. Lenz was the advisor and Ising was the PhD student at that point of time. And Ising gave his exact solution in space dimension 1, and they couldn't find any. As you all know, there is no phase transition for non-zero temperature in Ising model in 1 dimension. And then for a period of time, it was thought that Ising model is of no use for the studies of phase transition until in 1944, Lars Onsager gave its solution in space dimension d equal to 2. People realized that there is this model is very important in the context of for studying phase transition. Okay, so in d equal to 2, it's on square lattice. Say the critical temperature is 2.279 approximately, and then later important calculations were performed by C.N. Young, Michael Fisher, and several others, and then 3D problem remains still unsolved. It's one of the major problems in the domain of physics, irrespective of, not only statistical mechanics. It is a fundamental problem in the whole domain of physics. And then the 3D case is basically, but we know a lot about it from the application of renormalization group theory as well as computer simulation and related finite size scaling analysis. We will present results primarily from this model and a generalized version of that is known as the Potts model. So here is the phase diagram for the Ising model. So this x-axis is the magnetization, and this is my temperature. At high temperature, where thermal fluctuation, the temperature effect dominates, you have paramagnetic phase, and at very low temperature, so at t equal to 0, from the Hamiltonian, when J is positive, you can figure out that the energy gets minimized. Then all the spins are actually aligned; they're parallel to each other. So there is an order. So at low temperature there is order. At very high temperature there is disorder. At high temperature entropy wins, and in between there has to be something, some temperature at which this transition from order to disorder takes place, and that's the critical point. So we prepare our system above the critical temperatures, temperature at various different temperatures. We call it TS, the starting temperature. And then quench all those systems to a common final temperature, TF, final temperature TF, and TC is the critical temperature. And this TF could be 0 or anything below TC. Okay, and so overall, this is a problem that belongs to the non-equilibrium domain. It's the coarsening phenomena, how starting from a paramagnetic phase, a magnetic system, in this case, uniaxial ferromagnet. That's because our spins can take values +1 or -1. Okay, it's one axis basically. So how such an uniaxial magnetic system starting from paramagnetic state equilibrates or coarsens to a new equilibrium following quench to a temperature TF starting from various different temperatures TS. And we felt that the considered system, this Ising system, a priori appeared to us to be good candidate for exhibiting the Mpemba effect. And the question then you may ask why. I'll come to that point later briefly. Okay, so these are some results then from Monte Carlo simulations of my student Nalina. And here what we plot, this is the plot of energy, that is your, according to your Hamiltonian that I had written down in the first slide. I used the symbol H there, and as a function of time. So your time counting starts as soon as you quench your system to TF. So it's basically instantaneous quenched, as if the system immediately after the quench is assuming the value of the final temperature. Okay. And then this is how the energy is decaying for various different starting temperatures. So the upper panel within this whole graph contains results from early time, relatively early times, and the lower one is from late times. So at early time, what you can see, the energies are higher for higher temperature. So highest temperature is 2.8 in appropriate unit. Okay, you can see that the potential energy is highest for this highest temperature and lowest for this lowest temperature 2.3. So this is the closest one we have considered in this figure, that is closest to the critical point. Everybody can hear me?
Yes, yes.
Yes, sir. Okay, very good. And now we go to late time. You can see that the order has reversed, right? What was blue at the top, that has become that is appearing at the bottom, and the sequence is exactly opposite to what is in the upper half part of the frame. Okay, so that means there has been a crossing. Okay, that means the starting temperatures, the temperature for which the systems for which the temperature is higher to start with. Okay, they are approaching the new equilibrium faster than the lower ones. That means that says that there is Mpemba effect in the system. And same thing. So typically, what you do when you study coarsening phenomena, domain growth phenomena, okay, non-equilibrium evolution. Okay, when you quench your paramagnetic system to a temperature inside the critical point, so this state is no longer a stable state here. The system is falls unstable to fluctuation, and then it tries to reach the new equilibrium that is provided by the thermodynamic parameters here. Say at this temperature, it will have a ordered configuration, not completely disordered like in the paramagnetic phase. So that means it is evolving from one type of configuration to another. Okay. Paramagnetic configuration. Paramagnetic means your net magnetization in the system is 0, and ferromagnetic means you have ordered states, so your net magnetization is non-zero in the system. Okay, and so in such studies, what typically is done, or what happens typically, I'm going to a later slide to show you. So after the quench, domains start forming, and those domains grow with time, and you calculate the size of the domains as your system grows, okay, or evolves towards the, or gets closer and closer to the new equilibrium. Okay. And so that's what is plotted here, average size of domains as a function of time. And you can see at the beginning, the domain for the lowest temperature was highest, and that has become lowest at a later time. The highest temperature ones are approaching, they are growing faster than the lowest temperature. Okay. And this is a plot I don't want to discuss. This says that the crossings are very systematic, implying every higher temperature potential energy is crossing every other lower temperature potential energy for quenches to various different final temperatures. So one set of results are for 0 temperature quench, and another is for somewhat closer to TC, 0.6 TC. Okay. The question is then, what is the reason behind this observation of Pempenba effect here? For that, let me get into a little bit more formal definition of discussion of phase transition. Okay. So let us, phase transitions have different aspects. Like one is, there is a big domain called critical phenomena. And so this field was developed, so the critical phenomena exists from since more than 100 years back. Started with experimentalist engineers, and then in the 20th century, Landau gave a big boost, and following that, Michael Fisher, Leo Kadanoff, Kenneth Wilson, Benjamin Widom, they carried the field much forward, and to a great extent, this phenomena is understood, and there exists universality, so on and so forth. And so these are kind of common pictures related to phase transition that you are very much, all of you are familiar with. So this is a plot of the phase diagram of a normal chemical system in pressure versus temperature plane. Various different phases are marked, and they coexist along various lines. These are called coexistence curves, and this say liquid gas or liquid vapor coexistence curve terminates at a particular point known as the critical point. And if you take this small part, say, of the liquid vapor coexistence curve and plot it on a different plane, say temperature versus density, then you get such kind of a picture. So basically, you have a critical point here, and then there are two branches. One is the left branch and right branch, and they provide you information on the values of the overall density in the vapor phase and in the liquid phase as a function of temperature. And as your temperature is raised, they meet at a particular point, beyond which basically you are in the supercritical phase where there is no density difference. So that's why there is no continuation of this coexistence line here. If you cannot distinguish between two different phases, no point extending it further. And in the vicinity of this critical point, a lot of interesting things happen. So let me pictorially demonstrate it. I have copied these pictures, I think, from the book of Eugene Stanley. A lot of interesting experiments were performed. Some of them were performed in early days in space also. And so when you are at a very high temperature, then you have this supercritical vapor phase. It's in a test tube. You can see through the tube. And when it is inside the coexistence curve, you can see that your vapor and liquid phases coexist with each other, being separated from each other by the formation of this interface. And when you are close to the critical point, so there is this milk-like look, is called critical opalescence. Basically, it's very muddy kind of a look. So it's named after important this stone. It's called critical opalescence. And this critical phenomena has different sub-branches. One is static critical phenomena, and another is dynamic critical phenomena. Static critical phenomena is related to the behavior of various thermodynamic and transport properties in the close vicinity of the critical point. It's about thermodynamics and structure. Okay, and dynamic critical phenomena is about the transport properties in the system. What happens to the transport properties in the close vicinity of the critical point? So coming to the static critical point, so the primary point here is the central quantity here is the correlation length xi. That diverges at the critical point as a function of epsilon. So epsilon is kind of your deviation of temperature from the critical point. And so as you approach the critical point, you can see that this quantity tend to become 0. And so then there is a negative power here. It diverges. Nu is positive quantity. And the question is, what is correlation length? So for that, you have to calculate, or you have to look at the structure in the system. Like there is huge density fluctuation or order parameter fluctuation in the system close to the critical point, and by the calculation of this quantity, you actually pick up the structure in that fluctuation. And this correlation, this is the correlation function, and this correlation function has this Ornstein-Zernike form, Ornstein-Zernike-Fisher form. This P is a power law exponent anyway, and this xi, so when you are close to the critical point, xi diverges basically. So that means your decay of correlation becomes slower and slower when you plot it as a function of distance between the 2 points. Okay. And then coming to the transport property part, transport, I mean, dynamics is related to relaxation of a system, and in that relaxation, transport plays very important role. And transport quantities are like various different types of diffusivities, then viscosities, etc. And overall, so when your correlation length is very big, a system tries to relax, say, over that length scale, and when that length scale diverges, naturally your relaxation time also diverges. So it is written as a function of xi with some positive exponent z or z, whatever you would like to call. So that basically diverges. And then there is associated, okay, I'll come to that point. So I'm showing you the very old pictures that I showed you a couple of slides back. Now we are preparing our systems at various different starting temperatures above the critical point. So above the critical point, what is happening? We mentioned that the correlation length is diverging. Okay, and because of that, actually, this sort of milky-like behavior, the critical opalescence you can see here. And so there is basically fluctuation at all length scales. It's a little more complex than the way I'm saying. And so that you can visualize this fact from these computer simulations. So this is from a lower temperature and this is from a higher temperature. Okay, both are above TC. I told you for this 2D Ising model, the critical temperature is 2.27 approximately, and both of them are above that particular temperature. And closer one, 2.4, that has a larger length scale than the one at 2.6. These are typical equilibrium configurations prepared at these two selected temperatures. So there is a growing length scale as you are approaching closer and closer to the critical point. These are equilibrium, not evolving one. They are equilibrated. Okay. And then you quench these systems inside the coexistence curve. Okay, below the critical temperature, and then it is understood that in the asymptotic limit, at least, the average size of the domains. So remember this plot, I plotted average size of the domains, okay, the same quantity I'm talking about, that grows in a power law fashion following the quench with some exponent, say, n. Okay, so you have a paramagnetic phase disordered situation at very high temperature. Okay, and then finally the objective of the system is to reach this phase separated state in the context of magnetic system. So the whole thing will be one color. Okay, all spins are, say, when you are quenching the system to 0 temperature, everything will be either up or either down. But this picture I somehow put it here from phase separation in binary mixture. Okay, so there may be a little bit of confusion. So anyway, for whether it's phase separation in binary mixture or ternary mixtures, or in a para to ferromagnetic transition, during para to ferromagnetic transition, it is expected there will be power law growth. Okay, and this power law growth we expect actually to start immediately, almost immediately, quote unquote, when your configuration is perfectly random. That means you are starting from infinite temperature. Okay, but when you quench, so these configurations are actually slightly quite a bit different looking than this one. Okay, this one is prepared, say it's perfectly random initial configuration that mimics the extremely high temperature picture, the infinite temperature, theoretically speaking. So if you have such a starting temperature, you may expect the power law growth to settle in from very early time, but for such type of configurations, it may take some time for the system to forget this initial correlation in the system and adopt this behavior. So there will be a crossover, and that crossover time may depend upon the extent of initial correlation in the paramagnetic phase. Okay, and then how that memory of the initial configuration is lost in the after the quench, that depends upon, I told you about this dynamic critical phenomena. So this is perhaps, this is actually, so this relaxation time is the time when you quench an infinitely disordered system to a temperature close to the critical point, depending upon the size of the final equilibrium correlation length size, how the system goes to that equilibrium state. Okay, now after preparing this system with the same correlation, you are quenching the system to a temperature below the critical point, then it will try to forget what it had built to start with. It will try to forget after the final quench. So there are two steps. There are two steps in this process. Once you prepare a system from random configuration to another temperature by quenching it to another temperature above the critical point, and there it relaxes with some exponent z, depending upon the value of the and the time depends upon how large the final correlation length is. And with that that system with that correlation length you quench below the critical point, then you see how another evolution takes place. In that second step, it will try to, before actually settling down to this power law growth with respect to time, it will try to forget this correlation length. Now, the building up had occurred with exponent z. In fact, with respect to time, with exponent 1 over z, xi goes as tau raised to the power 1 over z. So there is a competition between two exponents. One is related to the loss of memory 1 over z, and another one is the final asymptotic growth with exponent n. And typically for all the known systems that I am aware of, 1 over z is less than n. And if that is the case, there is going to be crossings like what I demonstrated very schematically, and that's typically what you see here. Okay, and but that's not the only story. There may be more to it. But we are working to understand what exactly happens. There are much more to what I said. Okay, and the same exercise or exercises have been performed by using a more generalized version of the IG model that is referred to as the POTS model. So in this case, another student, Sohini Chatterjee, is also involved. So here POTS model represents multi component mixture. Okay, so it can mimic a magnetic picture as well as multi-component mixture exhibiting phase separation also. But here we are dealing with the magnetic case. In that case, basically, instead of taking +1 and -1 values, you basically designate the spins as 1, 2, 3, 4, 5, etc. Okay, and then for that number, total number of components, you represent by, for that you use the symbol Q, and for Q greater or equal to 4, for large Q, this, so I discussed the critical point phenomena. This critical point is actually second order point of second order phase transition. At POTS model for Q large, it exhibits first order transition. And here these results are for q equal to 5, and you can clearly see that there is crossings here also. But I don't want to get into the details of that again. Rather, I come to the conclusion. I was asked by my friend to be within the time limit of 45 minutes. So I probably marginally crossed that. So here are my conclusions. We have demonstrated Mpemba-like effect in simple Ising or Potts model with non-conserved dynamics. So here, let me tell you very briefly about what is non-conserved dynamics or what is conserved dynamics. So when you consider a binary mixture, for example, a mixture of oil and water, they can phase separate, all of you know. And then you start them, for example, they are mixed. And after a while, if they are in favorable thermodynamic condition, external condition, then they would like to, on one side, there will be completely oil and water will occupy the other side. And in this process, what has happened? So oil particles remained oil and water particles remained water, but they just shifted their locations. That way, basically, the phase separation has happened. On the other hand, in the case of a magnet, okay, suppose if you are quenching your system to 0 temperature, then what do you expect the final thing to be? All the spins are aligned parallelly, okay? They're all parallel to each other. But you have started with this from a paramagnetic situation when the spins are randomly aligned, so 50% are up and 50% are down. So that way your net magnetization was 0, and you ended up with a situation where all spins are aligned in along the same direction. So that way, the total value of the magnetization in the system has not been respected over time, so it's not conserved. On the other hand, in the case of phase separation in a binary mixture or ternary mixture for multi-component mixture for that matter, the A particles remained A, or oil particles remained oil, and water particles remained water, but they just moved their positions. They just shifted their positions. That's what is non-conserved. So non-conserved applies to magnetic system and several other systems also. Yeah, and I discussed a possible scenario, but it requires further investigation. And very interestingly, so I told you about this conserved and non-conserved dynamics. We observed it for non-conserved dynamics with Ising and Potts model, and we are struggling to observe the effect for conserved dynamics. And it is another puzzle irrespective of whether it is related to loss of memory of initial correlation or freezing during coarsening. And we have also made some progress on water. And if finally we are sure that our computer simulations are actually producing the Mpemba effect, at the moment we are more than partially sure. So then we'll parallelly, basically, we are investigating whether it can be because of the same structural feature that I have discussed in the context of magnetic system. And remember that in this case, it is a first order transition, okay, as opposed to the Ising case where I discussed the case of second order phase transition. And this is a list of students who are engaged in Mpemba effect related studies in various different systems. And with that, I come to the end, and thanks again for listening. Yeah, I'm done.
Thank you very much, Shubir, for delivering this wonderful talk. And these kind of phenomena and what lies at the core of this phenomena always catches more than the fancy of our imaginations. And I'm pretty sure that the students have well appreciated it. So it was actually very nice. In fact, I am myself very much interested. I was feeling very much interested while I was listening to your lecture. So there was one thing is that whether there are two kinds of studies, like say studies with real material, experimental studies, and maybe the studies are the model studies like Ising model, Potts model, various kinds of first order, second order phase transitions. So in your talk, it seems to be the case that this could be quite an universal phenomenon, skipping over the order of phase transitions. That
Yeah,
is
right, right. As of now, that's what seems to be the case. And we need to investigate basically whether such order should matter at all. Okay. Whether it is very trivial or not. But as of now, the whole thing is the way people took it initially. It was certainly, or it is still very non-trivial. The overall fact that the phenomena is there, and so a long way to go, I guess. Yeah.
Yeah. It's actually, I was wondering whether it was due to some kind of material properties of water versus maybe say if you use alcohol, maybe some other kinds of effects would be there. Maybe the
Yes.
kind of forces which are because I was it quite get quite caught in the topic because it's near to one of the my favorite topics, which is the cosmological phase transitions.
Hmm.
I was wondering whether what would be the implications of that for this,
Hmm.
and that
Yeah, yeah.
implications could be a lot. In fact.
So yeah, yeah, absolutely. So this cosmology, I mean, it did strike me also. I was thinking if I could collaborate with somebody from that area, and you'll be surprised. Actually, I actually intended to do this study in active matter systems. And active matter systems, we see all flying birds, fish. We love
Yes,
to
yes.
eat and also love to watch the clustering phenomena that fishes do exhibit under the water. So we human beings are also active particles, basically. So they also exhibit phase transitions, and that is another area of my strong interest these days. And so I was thinking of investing it in active matter systems, and so somebody who I know actually already did something. It exists in active matter systems also.
Oh, that's very fascinating to know.
Yes.
So, thank you, Shubir, once again. I was expecting questions over here, but I do not know whether due to network.
Can I ask some
Yeah.
questions, Shivaji?
Yeah. Sir, please.
Okay. So, Shubir, first of all, as usual, it was a great talk. But there are a number of questions which I was thinking. First question, a very general question before I come to the technicalities. Do we understand water?
Very little.
I mean, there is.
And first of all, let me tell you, I'm not an expert in water. So water studies I studied very recently in the context of Mpemba effect. But as far as my understanding by talking to various experts in water goes, from that I can tell you that we'll understand very little about water.
Well,
Yeah.
I mean, let me tell you. I mean, when I was talking to Michele Parinello, for example, as you know that he has worked so much on the molecular dynamics of water. Okay. Now, right in the beginning of your talk, you showed some EAB kind of interatomic potential, and you know that it is far from being true. I mean,
Yeah.
the expression which you showed. I mean, it's known that this is an empirical. I mean, water cannot be described, or I mean, by that kind of a simplistic empirical kind of a potential, because the so-called potential energy surface is much too complicated. But the question is that when you are talking about the Mpemba effect, one thing is that you went through, as a professional statistical mechanist, you went through your Ising model. I mean, and after that the 2D avatar of Ising model and things like that. Now, is it that the problem at d equal to 3 is something which is eluding us? Is it because of the fact, one of the reasons is that it is really a NP hard problem, and that is why we cannot handle it?
I can quote you from one of the last papers that Michael Fisher wrote. So he passed away by the in November, and so he was my postdoc advisor. And then, so this is a little controversial issue, but I mean, not really controversial. So somebody actually wrote some conjecture solution of Ising model that was published in a well-known journal from England. I don't want to quote those names. And he claimed that he has a great solution. Okay, and it was 111-page paper. And probably he thought that nobody will read that paper so carefully. And so then it caught eyes of some statistical mechanicians who are hardcore analytical people, then brought into the notice of Michael Fisher, and then he went through it very carefully. Then they wrote a paper, obviously negating the outcome of the published paper. There, this NP hard problem is not mentioned. It is mentioned that it is an outstanding unsolved problem of physics. So that's what I can tell you.
Okay. And the last question, because there are many, maybe others too. See, that is a more, sort of slightly technical. See, you mentioned about the static versus the dynamical critical phenomena. Okay. The question is that for Mpemba effect, I got a bit lost when you mentioned about the growth coarsening of the AB kind of a system. How does that gets related to the Mpemba effect? Because that is something which I know. I mean, this growth coarsening thing which you mentioned, the different domain structure and how the AB separation. But in Mpemba effect, how is that related? I mean, can you just make any comment on that?
Yes, probably I was not so clear. So when you quench the system, so see here we are preparing the temperature systems at different temperatures above the para to ferro transition, and then quenching each of those systems to a temperature below the critical temperature, that is ferromagnetic region. So after the quench, the system will finally evolve towards all ordered, right? And that will happen by the formation and growth of domains. And now there will be some transient period, early time period, during which the dynamics and structure formation will be different for different starting temperatures. So eventually in the long time limit, if we go by renormalization group theoretical picture, eventually this T raised to the power n behavior with unique value of n will be recovered. But how the early time behaves in that after the quench, depending upon your starting temperature, that is the deciding factor. But how exactly? So yeah, I need to know more.
Yeah, and the last one, the dependence of the relaxation time on the initial temperature. You mentioned that in the beginning, towards the beginning of your talk. Okay. Now, in this particular example, is it that it is known that how the relaxation time depends on the initial temperature? Do we know explicitly how?
Yeah, so it goes as power law. So if you start, for example, from perfectly disordered configuration, say perfectly random initial configuration, then when you quench to lower temperatures but above the critical temperature, then finally you expect the correlation length xi to be function of this final temperature. Okay, but above the critical temperature. So then it goes as relaxation time goes as whatever the final relaxation correlation length you expect, that raised to the power some exponent. So that's the primary dynamic critical exponent.
Okay, thank you. Thank you,
And
Shubham.
that Z has different values for different models. So that Z, the exponent is not as universal as the static critical exponents like nu and other ones. So there, for example, in the static case, if you calculate nu for Ising model, so there is Ising universality class, say 2D universality class, 3D universality class. You study, say, oil-water mixture, or para to ferromagnetic transition or vapor liquid transition. In each of the cases, if there is a critical point, the value of the correlation length exponent nu or the susceptibility exponent gamma will be same. But for each of, at least two of these cases, these examples, in the magnetic case, the dynamic exponent Z will be different from the others. So in the dynamic case, the universality is less robust.
Okay, thank you very much, Shubir. Yeah, we'll talk later again. Yeah, so
Yeah,
there are
sure.
other questions. Yeah, yeah.
Okay, so can I ask a question?
Yeah.
Please go ahead.
Kaushik.
Go ahead. Kaushik.
Yes, yeah. So my friend Indranath is insisting me that I should make a comment and ask a question, and I must say that it's a great pleasure to listen Dr. Shubir Das's talk. It was one of the best talks I have ever heard, and to mention two things, I have a short question. And before going to the question, I must say that this is a fascinating talk. The most important thing that I get from this talk is that a small school student can initiate a big journey, right? So one of the simple observations in a high school, and this observation led to big scientists taking up this idea and taking up this subject matter. It opened up a new field, so to say. And it was named after the student, high school student, Mpemba effect. And even Nobel laureates eventually joined in, and then they started working on that topic. So, and this paper was initially not published in a very high impact factor journal. So whether it matters, whether we put too much emphasis on what journals these works are published, who is publishing it. Sometimes we put too much emphasis on these things before taking up a problem. So this is one important thing that our students should always think about when taking up a physics problem, that it does not really matter. Even a high school student in Tanzania can initiate a problem which should be studied all over the world, even the Nobel laureates and Nobel laureate like scientists. So that's a very, very important message Shubir has delivered. And this is important for the students in India, especially colleges like St. Xavier's College and other colleges, where in my experience, if a high school student or a college student observes something, we don't normally take that observation on the face value. There in Tanzania, an university professor, when heard that problem asked by a high school student, he took it seriously. So that is also a very important lesson for all of us, that simple, small observations may lead to huge, big problem, physics problem. So that is one thing. And I must thank Shubir for initiating so much curiosity. And this is an example of curiosity-driven research. One of my silly questions is, normally we see that Stefan Boltzmann type of radiation, it goes as T to the power 4, where T is the temperature difference between the substrate and the ambience. So that means that the heat transfer will be faster when there is a huge temperature difference. So what is the effect of that? So this is when you start with hot, like boiling hot water, obviously the temperature difference is much higher than a colder body, like a room temperature water. And that means that the rate of heat transfer will be much faster in the hot object. And it would reach 0 degrees Celsius. The freezing point could be much faster, and eventually the phase transition will take over and it will freeze. So where we are, I mean, is this like?
So can I? So thanks, Kaushik. So this is not a silly question. So this what you're saying is black body stuff. But in general, I mean, people ask question whether Newton's law of cooling can explain this thing. So it's along the same line. But, so when you start with two different temperatures and the objective of the system is to reach at the same final temperature, so there will be a crossing. And at the crossing point, there has to be a crossing. And at the crossing point, you have the same temperature on the way to the final temperature. And what after that? So this way, if we proceed, then basically the Newton's law of cooling actually could not explain the phenomena. People thought hard about it. So I actually gave this example. This then the evaporation and all those things will take place because of the starting higher temperature, etc. But all those things kind of were unsatisfactory, and the primary point is that in theory what we are doing here, we are actually performing instantaneous quench. Even that gives rise to this fact. You can say that the theories are far away from often the actual experimental scenario, but yeah, you need to approach in various different ways first and see what is happening. So for the time being, I can say that even if you do, so for example, if all the Monte Carlo protocols are correct, so there are also deficiencies in all the various theoretical and computational tools. And but the similar tools are reproducing various other facts. So you have to believe them at, yeah. To
I understand that this is in real life there are so much impurities, and
yes.
And in phase transition the fluctuations in an ideal system fluctuation is something, and in real life when there is impurity or some perturbation, fluctuation can differ, right? I mean, So it's a metastable state. So from metastable state, when you transition to another state, so the fluctuation would grow, and in presence of impurities or any other perturbation, small perturbation, it may lead to another stable state or metastable state. So,
So yeah, all those things are there. Let me. So the metastability is a very complex thing. Okay, and I heard many big people asking very interesting short questions to some other slightly lower level of big people who are talking on metastability. So, what is metastability? Then those relatively smaller fellows just stopped giving the talks, basically. So metastability is such a thing not many people understand clearly. I'll tell you a story. So this story I was told by Michael Fisher, and Fisher heard from Joel Lebois, and Joel Lebois is a postdoc with Lars Onsager. So Joel Lebois, when he was a postdoc, he asked Lars Onsager, Lars Onsager actually lost his job because he was a bad teacher. He was not such a. So I'm actually, this thing is on YouTube. I'm probably not telling correct stories here. Anyway, but he was an extraordinary physicist. So without him, physics, chemistry, engineering, I mean, nothing can move a few steps forward. So his answer was, okay, once. So in Canada, in some place, there was a glycerin industry. And one fine morning, nucleation started and all the pipes broke. So that was his answer to metastability. So what I do not know, I mean, whether the students are able to gather some information from metastability. So I'm also diverting from your actual question, but I think it's something good to know. So what he intended to say that the waters in Canada is very cold, of course, most time of the year. And so then water has a lesser volume than ice. So on normal days, even at very low temperature, this water actually is in metastable state. Freezing does not occur. Okay. Then the water smoothly flows to the pipes. And then someday, because of some impurity or whatever, there was heterogeneous nucleation. And once nucleation happened, it propagated throughout the pipe system. And volume increased and the pipes broke. This simple statement, if you look differently, this actually tells you a lot of things, actually. So anyway, coming back to the point, because of metastability, experimental observations also differed. So I quoted from some paper, so no complaint to the authors of the paper, but experimental, some experiments did observe, some did not. It depended upon what kind of impurities you have in different regions on the earth.
Exactly.
Different sorts of impurities are there, but then this experiment, that was the video that I showed, that was performed in Canada. So it was extremely cold, less than minus 20 degrees Celsius. That basically, I mean, beyond doubt, it has proven that the effect does exist. And if you perform the same.
So I can vouch for Canadian temperature because I was there for 9 years.
Yeah.
So minus 20 is very normal there.
I have a naive question, Shivaji, that can I ask Professor Das?
Yes, go ahead.
Professor Das, I'm Shuparna Rai Chaudhary from the physics department.
Hello.
Actually, I don't know. It's probably a very naive question because I just got introduced to the Mpemba effect from the abstract that I read when we were making your poster, when you actually sent it to us. And then I was sort of looking up. Actually, what intrigued me was, I mean, of course, from whatever you have told us, I was just wondering, see, so there is a huge temperature gradient, right? When you're cooling from hot, a very hot, I mean, situation to 0, let's say 0 degrees centigrade, whereas the temperature gradient coming from, let's say, close to 0 would be smaller. So I was just wondering, like, you know, what sort of effect convection currents would have, like, you know, in these two different, you know, samples, one be having a delta T greater and the other having a delta T smaller.
Yeah. So is the question similar to what Kaushik asked?
Yeah, I think, exactly.
Yeah. So you need to say, the temperature which is further away, there is a stronger drive towards the new equilibrium following coins to the same final temperature. But the point is that at some point of time, so if the system starting from higher temperature, it is trying to cool down at a faster rate, at some point it has to cross the lower temperature one, right? And at that point, the drive becomes same. Right. So this is one way of thinking. And the other thing is, say, we are in theory and computer simulation are dealing with instantaneous quenches. Even then, we do observe it. So that is interesting, and it's not a naive question like Kaushik. It's the question that both of you asked is very important, but further studies are needed. So these are some hand-waving things I'm saying, but the other people also thought hard along that direction, but they could not arrive at any much satisfactory answer. In any case, further investigations are needed.
Yeah. Is it like sort of related to the fact that it, after having cooled down, like let's say to 0 degree, in both cases, you know, the formation of ice, that process is like the one which is sort of making the difference, even though, like, because the drive is coming.
So actually, both are perhaps responsible.
Okay.
So if you go to give a Google search with Mpemba effect, you will come across a picture on your right hand side that will show you the this cooling rate.
Yeah.
Okay, and I believe what your second point is after reaching the final temperature, there also it is faster.
Yeah. I was
So
just
both are
wondering
there.
because see, I work in astrophysics, and I teach students about convection in the sun, and we are talking about regions where there is radiative transport because it is in equilibrium, and regions where these are far away from radiative equilibrium, and where there is a lot of convective current setup, which essentially transports energy faster and equilibrates faster and brings it back to radiative equilibrium. So I was just wondering, like, whether such a thing is also, sort of possible to observe in places like sun, and I mean, so
So I actually asked myself also similar questions, but I do not know anything about cosmology, astrophysics. I have to learn those things. Not that I know the other subjects so well, but yeah, I know much less in
thank
that
you so
domain.
much. In fact, it was a very intriguing talk, and I think it sort of set up a lot of intriguing questions in our minds, I guess.
Thank you, thank you.
Let us take up the question which is in Zoom. So maybe Shubhadeep, you I may ask your question now. Shubhadeep De.
Am I audible?
Yes.
Yes, you're too much audible.
Shivaji, once you allow me to speak, I'm Tapti here, okay? So, sir, my question is, does the Mpemba effect works in reverse?
Yeah, there are actually reports of reverse Mpemba effect also. Yes, yes. But it may not be true for all systems, but some groups reported that there exists reverse Mpemba effect also. Yes.
Okay.
Thank you, sir.
Tapati has a question.
So, yeah. Thank you, Shivaji, and thank you, Dr. Dash, for telling us about this effect. My question is something related to one of the slides you showed right at the beginning. When it was a slide, if you scroll back, there was one slide which had your some screenshot of what the, black and white, red and blues all randomly placed, whatever you placed, and then there was this the equilibrium state where your
Can you see
simulation
my slides?
no, but previous to this, much earlier on, where you had an arrangement much earlier on. This one, please.
Here?
Next one, I suppose. The next one, yeah. Please hold on. This one, yes, exactly. So I want to know this sub-zero T, where there is this arrangement of this lattice, starting from there, coming to here, which is a very ordered, space-filling, almost hexagonal, regular lattice. So,
Yes.
so I want to ask you, what is there? How did what is the physics? Is it energy minimization? How would you?
It is energy minimization.
Yeah. And so, but you did a Monte Carlo simulation.
No,
So
this is molecular dynamics.
molecular dynamics, where you are moving towards energy minimization by checking every step, right? That whether it is energetically supported. But
no, the system is creating the structure on its own, and when it is moving from one structure to the other, then there is all of a sudden some drift in energy.
True. But what I want to know is why the hexagon?
Yeah. So, but what is it shows different types of structures also. That is to some extent temperature dependent. There exists square type structure also in water.
but you obtained a square space filling sort of a structure for energy minimized condition at equilibrium, or
Yeah,
was
so
it?
if you vary the temperature, you may actually see other structures also.
Yeah, to be very specific, I want to know, did you, forgive my insistence, because, you know, I am also working on certain areas where it seems that we all know that for a given area, the hexagon is for a regular polygonal structure. The space filling lattice, the ideal sort of the minimum perimeter length is the hexagon. So I was just, you know, for a given area, if you have to fill up a 2D tiling, you know, with space filling tiles, which are absolutely convex polygons, regular, then it has to be an hexagon that minimizes the energy. So, so that can be proved. So I was wondering whether what is there, I mean, that
So
geometry.
it is basically the free energy minimization.
Did you,
So,
is it something related to Ginsburg-Landau sort of a macroscopic theory, or?
yes. Something similar you were talking about. So there are debates in hard sphere systems, for example.
Hard
What
spheres
kind of
will not be space filling, sir.
no, but there also similar debates did exist, like what kind of structure, crystalline structure you expect. So there also things are done computationally, and then people basically look for which structure minimizes the free energy. So it's, as you said, it's the Ginsburg-Landau. So it's not Ginsburg-Landau. So Ginsburg-Landau is related to non-equilibrium stuff, and here we're searching for equilibrium structure. So say some sort of relevant free energy depending upon the thermodynamic conditions, what you keep constant and all those things. So it is the minimization of the free energy that will tell you what structure is more favorable. And their temperature has a role to play.
Okay, thank you.
So if there are no more questions, I thank the speaker once again for the wonderful experience that we had by listening to the talk, and I hand it over to the MC now.
Thank you, Dr. Banerjee. And thanks a lot, Professor Das, for the wonderful talk. Like, we really appreciate having this mysterious area clarified. Thank you, sir. And we have a link in the Zoom chat box as well as YouTube chat box for the feedback form. So the audience can fill it up.
So am I allowed to leave now?
Just before leaving, if the students, you have questions to Professor Das, so I can provide you his email address, and I hope that Shubir will answer, because there will be lots of questions. Maybe it is not asked here in this particular platform, but they can write to you, if you allow me, Shubir.
Yeah, sure.
So thank you, Professor Das, for your time. It's a wonderful
Thanks,
experience.
and all the best to the rest of the event, Spectrum.
Thank you.
And send a copy of your Horizon.
Yes, I'll send you. I'll send you, and I request you to visit our department when you come next, because once you have visited some years back, so we'll happy to host you here in the
department. Sure. Bye.
Bye. Thank you.
Thank you, Shubir. Bye-bye.
Bye.
So in the past couple of days, we have had some very entertaining inter-college events, and now it's time to declare the results. I would like to call upon Abhinandita Sinha, the convener of Spectrum 2022, to do the honors.
Thank you, Raktim. Hello, am I audible?
Yeah.
Okay. So we had various events for the past few days for Spectrum 2022. The results of them are as follows. First, we had the chess tournament named Conquer the Squares. In the first position, we have Ambarish Sharma from St. Xavier's College. Second position, we have Prem Arpan Tirke from St. Xavier's College 2. And in the third position, we have Shudipa Haldar from St. Xavier's College. Up next, we have the results for the treasure hunt event, that is World of Physics. We have the winner, that is Ashmita Mondal from St. Xavier's College. Next, we have the results for debate, that is War of Wits. We have the winners, Agnideep Chakraborty from St. Xavier's College, Justin Williams from St. Xavier's College, and Dipannita Mishra from Midnapur College. Last of the events, that is the circuit simulation event, Build Your Bits, and the winner is Agnideep Chakraborty from St. Xavier's College. Thank you. We are having a small technical glitch at this point of time. We are fixing it as soon as possible. Please be patient. Thank you. Sorry for the glitch. Up next, we have the cultural event that is going to be held. So we have had this in the pandemic. Therefore, we have a stream of pre-recorded videos from the students of our very own department. So please hold on and enjoy the event. Thank you.
মধুর মধুর ধ্বনি বাজে হৃদয় কমল বন মাঝে মধুর মধুর ধ্বনি বাজে হৃদয় কমল বন মাঝে মধুর নিভৃত বাসিনী বিনা পানি অমৃত মূরতি মতি বাণী নিভৃত বাসিনী বিনা পানি অমৃত মূরতি মতি বাণী হিরণ কিরণ ছবিখানি পরাণের কথা সে বিরাজে হৃদয় কমল বন মাঝে মধুর মধুরিত জাগে দিবানিশি পিক কুহরিত দিশি দিশি মধুরিত জাগে দিবানিশি পিক কুহরিত দিশি দিশি মানস মধুপ পদ তলে মুরছি পড়িছে পরিমলে এসো দেবী এসো হে আলোকে একবার তোরে হেরি চোখে এসো দেবী এসো হে আলোকে একবার তোরে হেরি চোখে গোপনে থেকো না থেকো না থেকো না গোপনে থেকো না মনোলোকে ছায়াময় মায়াময় সাজে হৃদয় কমল বন মাঝে মধুর মধুর ধ্বনি বাজে হৃদয় কমল বন মাঝে মধুর
You have to believe in yourself. You have to believe in your ability. You are capable of anything. You can achieve any dream. Please don't limit yourself. Don't live your life limited. It's not a sadness and misery. Life's a challenge, but you will succeed. Take control of how you feel in every circumstance. Work on yourself daily. Your story's far from done. The best is yet to come. achieve, you must believe. You can live out all your dreams. Persevere, you make it through. What you need is all in you. When you believe, you will achieve. You can live out all your dreams. It's about time you knew it's true. God got power all in you.
আমরা শুভ দাশগুপ্ত। ক্ষুদিরাম হবে পাশের বাড়ির ছেলে, আমার ছেলে ডাক্তার হবে, আমার ছেলে ইঞ্জিনিয়ার হবে, নিদেন পক্ষে সরকারি অফিসার। ক্ষুদিরাম হবে পাশের বাড়ির ছেলে, আমার ছেলে দেশ চালাবে, দেশ শাসন করবে, গাড়ি চাপবে, সামনে ড্রাইভার, পিছনে চাবরাশি, আদার্স। গরমে কুলু মানালি, শীতে কোভালাম বিচ। ক্ষুদিরাম হবে পাশের বাড়ির ছেলে, দেশের জন্য লড়াই করবে ওপাড়ার ওরা। আমার ছেলে ঘাড় গুজে কেরিয়ার বানাবে, বিজ্ঞান শিখবে, অঙ্ক শিখবে, কবিতা শিখবে, বড় বড় মনীষীদের জীবনী পড়বে, দেশের জন্য মুখে রক্ত তুলবে ওপাড়ার ওরা। আমার ছেলে আমার রক্ত জল করা পয়সা সুদে আসলে উসুল করবে। নেতাজি সুভাষ হয়ে দুরন্ত দুঃসাহসে ঘর ছাড়বে অন্য কেউ। আমার ছেলে নেতাজির জীবনী লিখে অ্যাওয়ার্ড পাবে। ক্ষুদিরাম হবে পাশের বাড়ির ছেলে। আমরা তামাকে এবং দুধে, রসে এবং বসে, সুখে এবং আরামে দিন কাটাবো। দেশের মুক্তি প্রাণের মূল্যে কিনে আনবে অন্য কেউ। আমরা মুক্ত স্বদেশে ঘাড়ে পাউডার লাগিয়ে গদগদ কণ্ঠে গণ সঙ্গীত গাইব। সারে জাহাঁ সে আচ্ছা হিন্দুস্তান হামারা। ক্ষুদিরাম হবে পাশের বাড়ির ছেলে।
This is a composition by Pandit Udadev.
কিছু স্বপ্ন, কিছু মেঘলা, কিছু বইটই ধুলো লাগা, কিছু ইচ্ছে সারা দিচ্ছে এই বসন্ত রাত জাগা। মম চিত্তে পাশ ফিরতে আজ পলাশ ফুলের কাব্য নিতে নিতে ফুল ছিঁড়তে শুধু তোমার কথাই ভাবো। আজ হাওয়া মে পড়াওয়া দিল সন্ধে পাখির ঝাঁক, এই বিকেল আর বেল ফুল হৃদ মাঝারে থাক। নীল দিগন্তে ওই ফুলের আগুন লাগলো লাগলো, নীল দিগন্তে বসন্তে সৌরভের শিখা জাগলো বসন্তে নীল দিগন্তে।
सरगम हमसे बने, नगमे हमसे जवां, झूमे आसमां, अरे हम ही तो दुनिया के साथ अजूबे हैं, हमसे है जहां। जिंदगी मिलके बिताएंगे, हाल दिल गा के सुनाएंगे। हम तो सात रंग है ये जहां, रंगी बनाएंगे। जिंदगी मिलके बिताएंगे, हाल दिल गा के सुनाएंगे। हम तो सात रंग है ये जहां, रंगी बनाएंगे।
থাক তবু ভুবনে ধুলি মাখা চরণে মাথা নত করে রব। বসন্ত এসে গেছে, বসন্ত এসে গেছে, বসন্ত এসে গেছে, বসন্ত এসে গেছে।
ये मस्ती के नजारे हैं तो ऐसे में संभलना कैसा, मेरी कसम जो लहराती दगड़िया हो तो फिर क्यों ना चलूं मैं बहका बहका रे। मेरे जीवन में शाम आई है मोहब्बत वाले ज़माने लिए हो, चला जाता हूँ किसी की धुन में धड़कते दिल के तराने लिए। मिलन की मस्ती भरी आँखों में हजारों सपने सुहाने लिए हो, चला जाता हूँ किसी की धुन में धड़कते दिल के तराने लिए।
মোর ভাবনারে কি হাওয়ায় মাতালো, দোলে মন দোলে অকারণ হরষে। মোর ভাবনারে কি হাওয়ায় মাতালো, দোলে মন দোলে অকারণ হরষে। হৃদয় গগনে সজল ঘন নবীন মেঘের রসের ধারা বরষে। মোর ভাবনারে কি হাওয়ায় মাতালো, দোলে মন দোলে অকারণ হরষে।
ফাগুন হাওয়ায় হাওয়ায় করেছি জেদা, তোমার হাওয়ায় হাওয়ায় করেছি জেদা। আমার আপন হারা প্রাণ, আমার বাঁধন ছেঁড়া প্রাণ। ফাগুন হাওয়ায় হাওয়ায় করেছি জেদা, তোমার হাওয়ায় হাওয়ায় করেছি জেদা। তোমার অশোকে কিংসুকে অলক্ষ
পৃথিবীর মন ভালো নেই, মহামারী থেমে যাবে কবে? প্রতীক্ষা শেষ হলে দেখা হবে, ঠিক দেখা হবে।
পৃথিবীর মন ভালো নেই,
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 পৃথিবীর মন ভালো নেই, মহামারী থেমে যাবে কবে? পৃথিবীর মন ভালো নেই, মহামারী থেমে যাবে কবে?
প্রতীক্ষা শেষ হলে দেখা হবে, ঠিক দেখা হবে। প্রতীক্ষা শেষ হলে দেখা হবে, ঠিক দেখা হবে।
দেখা হবে, ঠিক দেখা হবে, দেখা হবে, ঠিক দেখা হবে,
দেখা হবে, ঠিক দেখা হবে।
দেখা হবে, ঠিক দেখা হবে। আবার ফুটবে জানি ফুল, কেটে যাবে ওই কালো রাত।
আবার নতুন কোন ভোরে
তুমি ঠিক বাড়াবে হাত, তাই তো এখনো ভালোবাসি, গান গাইয়া জন বলি।
আধার পেরিয়ে জানি আমি দেখা হবে, ঠিক দেখা হবে।
পৃথিবীর মন ভালো নেই,
পৃথিবীর মন ভালো নেই,
পৃথিবীর মন ভালো নেই, মহামারী থেমে যাবে কবে?
প্রতীক্ষা শেষ হলে দেখা হবে, ঠিক দেখা হবে।
প্রতীক্ষা শেষ হলে দেখা হবে, ঠিক দেখা হবে।
মৃত্যু তো শেষ কথা নয়, জীবনের জয় হবে জানি। মৃত্যু তো শেষ কথা নয়, জীবনের জয় হবে জানি।
তবু কেন এত সংশয়, চারিদিকে যত হানাহানি? সব থেমে যাবে, ঠিক দেখো,
মহামারী মুছে যাবে চোখে। পৃথিবীর
মন ভালো হলে দেখা হবে, ঠিক দেখা হবে। পৃথিবীর মন ভালো নেই, পৃথিবীর মন ভালো নেই, পৃথিবীর মন ভালো নেই, পৃথিবীর মন ভালো নেই।
ছাড়পত্র, কবি সুকান্ত ভট্টাচার্য। যে শিশু ভূমিষ্ঠ হলো আজ রাত্রে, তার মুখে খবর পেল সে পেয়েছে ছাড়পত্র এক। নতুন বিশ্বের দ্বারে তাই ব্যক্ত করে অধিকার, জন্মমাত্র সুতীব্র চিৎকারে। খর্ব দেহ নিঃসহায়, তবু তার মুষ্টিবদ্ধ হাত, উত্তোলিত উদ্ভাস, কি এক দুর্বোধ্য প্রতীক্ষায়। সে ভাষা বোঝে না কেউ, কেউ হাসে, কেউ করে মৃদু তিরস্কার। আমি কিন্তু মনে মনে বুঝেছি সে ভাষা। পেয়েছি নতুন চিঠি আসন্ন যুগে। পরিচয় পত্র পড়ি ভূমিষ্ঠ শিশুর অস্পষ্ট কুয়াশা ভরা চোখে। এসেছে নতুন শিশু, তাকে ছেড়ে দিতে হবে স্থান। জীর্ণ পৃথিবীতে ব্যর্থ, মৃত আর ধ্বংসস্তূপ পিঠে চলে যেতে হবে আমাদের। চলে যাব, তবু আজ যতক্ষণ দেহে আছে প্রাণ, প্রাণপণে পৃথিবীর সরাব জঞ্জাল। এ বিশ্বকে এ শিশুর বাসযোগ্য করে যাব আমি। নবজাতকের কাছে এ আমার দৃঢ় অঙ্গীকার। অবশেষে সব কাজ সেরে আমার দেহের রক্তে নতুন শিশুকে করে যাব আশীর্বাদ। তারপর হব ইতিহাস।
ভেঙে মোর ঘরের চাবি নিয়ে যাবি কে আমারে, ও বন্ধু আমার না পেয়ে তোমার দেখা, একা একা দিন যে আমার কাটে না রে, ভেঙে মোর ঘরের চাবি নিয়ে যাবি কে আমারে।
বহুদিন ভাব তরঙ্গে ভেসেছি কতই রঙে, বহুদিন ভাব তরঙ্গে ভেসেছি কতই রঙে, সুজানের সঙ্গে হবে দেখা শোনা, তারে আমার আমার মনে করি আমার হয়ে আর হইল না, আমার আমার মনে করি আমার হয়ে আর হইল না। দেখেছি দেখেছি রূপসাগরে মনের মানুষ কাঁচা সোনা, দেখেছি রূপসাগরে মনের মানুষ কাঁচা সোনা। বুঝি গো রাত পোহালো, বুঝি ওই রবির আলো, আভাসে দেখা দিল গগন পারে, সম্মুখে ওই হেরি পথ তোমার কি রাত পৌঁছবে না মোর দুয়ারে, ভেঙে মোর ঘরের চাবি নিয়ে যাবি কে আমারে, ভেঙে মোর ঘরের চাবি নিয়ে যাবি কে আমারে।
পথিক কয় ভেবো না রে ডুবে যাও রূপসাগরে, পথিক কয় ভেবো না রে ডুবে যাও রূপসাগরে, বিরলে বসে করো যোগ সাধনা, একবার ধরতে পেলে মনের মানুষ ছেড়ে যেতে আর দিও না, ধরতে পেলে মনের মানুষ ছেড়ে যেতে আর দিও না। দেখেছি দেখেছি রূপসাগরে মনের মানুষ কাঁচা সোনা, দেখেছি রূপসাগরে মনের মানুষ কাঁচা সোনা, ভেঙে মোর ঘরের চাবি নিয়ে যাবি কে আমারে, ও বন্ধু আমার ভেঙে মোর ঘরের চাবি নিয়ে যাবি কে আমারে।
Hello. Hello, am I audible?
Yes, you're audible.
So we are almost at the end of today's program. A lot of people have contributed to make Spectrum 2022 a success. I hope you have enjoyed it. I would call upon Dr. Shuparna Raichaudhuri to deliver the vote of thanks.
Thank you,
Over to you.
So as we come to the close of this year's edition of Spectrum, it was truly a wonderful experience. I hope that everyone in the audience enjoyed these last couple of hours, as our students have really put in their heart and soul to make this event a success. It is my honor to thank everyone who has been involved in the successful organization of today's event. I would like to start by thanking Father Principal, Reverend Dr. Dominic Savio SJ, for always encouraging us and supporting us, Vice Principal of Arts and Science, Professor Bertram Da Silva, Dean of Arts, Dr. Orgho Banerjee, and Dean of Science, Dr. Tapati Dotto, for always helping us with their valuable advice, Dr. Romit Beed from PPC and the PPC coordinator, Dr. Partho Pratim Ghosh, for all their help. I would like to extend my heartfelt gratitude to our speaker, Dr. Shubir Kumar Dash, for taking time out of his busy schedule and delivering such an amazing talk. Thank you, sir. We hope to see you in the campus soon. Next, I would like to thank the head of the Department of Physics, Dr. Indranath Chaudhary, for always supporting and encouraging such activities in the department, Dr. Sharbori Guho, Dr. Shudipta Roy, and Professor Gayatri Banerjee, and the student editors for painstakingly going through the whole process to make the 13th edition of Horizon possible, Dr. Tanaya Bhattacharya for sharing her memories of our dearest Nilangshu and taking us all down the memory lane, Dr. Shibaji Banerjee for conducting the technical session, Dr. Tapati Dotto for distributing the prizes of the, that was actually not Dr. Tapati Dotto, but later it was changed to our student, Abhinandita Sinha for distributing the prizes of the events, Dr. Sharbori Guho once again, Dr. Shonak Palit, Professor Gayatri Banerjee, Dr. Shanghamitra Das, and Dr. Shoma Ghosh for judging the different events of Spectrum, and everyone else in the department for always being there to help and guide the students. At this point, I would especially like to acknowledge the efforts of Ms. Abhinandita Sinha and Mr. Rupam Jash, both conveners, for spearheading the organization of Spectrum, and all the other student organizers in the different committees for making this event such a huge success. I would also like to acknowledge the efforts of the student performers and the participants of the different events in Spectrum for making all the events successful today. I cannot forget the contribution of our supporting staff and the technical staff of the computer science department, especially Mr. Shujit Shah, for lending their expertise for us to be able to organize such online events so smoothly. And last but not the least, our audience members on Zoom as well as YouTube, everyone who tuned in today to watch the event and be a part of it. I'm sorry if I missed someone unintentionally. We are truly thankful to each and everyone who has been with us in spirit and in person. Thank you, one. Thank you all. Stay safe and take care.
I want to thank Professor Suparna Raichaudhuri, because Suparna Raichaudhuri has thanked everybody. So it's my pleasure to thank Professor Raichaudhuri, Dr. Raichaudhuri, because her support, constant support to organize all the departmental events. She's our lab in charge also, so is doing great job for the department. Thank you, Dr. Raichaudhuri.
Thank you, Indrada.
Ruktim, you are muted.
Thank you, ma'am. Thank you, sir. And now I would like to request everyone on Zoom to turn on their videos for a group photo.